NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we solve a classic binomial expansion problem. We will count how many rational terms appear in the expansion of open parenthesis x to the 1 over p plus y to the 1 over m close parenthesis to the n. First, recall Newton's binomial theorem. Step 1. Express the general term in the binomial expansion. Step 2. When is a term rational? Exactly when both exponents are integers. That means 1, n minus k over p is an integer. 2, k over m is an integer. And 3, k is between 0 and n inclusive. We can rewrite these as divisibility conditions. K must be a multiple of m, and n minus k must be a multiple of p. Equivalently, k is congruent to 0 modulo m, and k is congruent to n modulo p. So we are looking for integers k that satisfy both congruences simultaneously. Here is the correct counting method. Let d be the greatest common divisor of m and p, and let c be the least common multiple of m and p. A solution k exists if, and only if d divides n. If d does not divide n, there are 0 rational terms. If d does divide n, then there is a unique residue r modulo c that satisfies k congruent 0 modulo m and k congruent n modulo p. All solutions are k equals r plus t times c for integers t within 0 to n. So the number of rational terms equals floor of n minus r over c plus 1, provided r is at most n. A common shortcut appears in a special case. If p divides n, then the residue r equals 0, and the count simplifies to floor of n over c plus 1. Be careful, that shortcut is not valid in every situation. It only works when r equals 0. Example 1. Let m equal 2, p equal 3, and n equal 6. Compute c equals least common multiple of m and p, which is 6. Here, p divides n, so r equals 0, and the count is floor of 6 over 6 plus 1, which is 2. We expect k equals 0 and k equals 6 to work. Example 2, counterexample to the naive shortcut. Let m equal 6, p equal 8, and n equal 9. The greatest common divisor is 2, which does not divide 9. Therefore, there are 0 rational terms. But the naive floor of 9 over 24 plus 1 would incorrectly suggest one term. Example 3, an offset case where r is not 0. Let m equal 4, p equal 6, and n equal 10. We have d equals 2, which divides 10, and c equals 12. Solve k congruent 0 modulo 4, and k congruent 10 modulo 6, which is k congruent 4 modulo 6. The unique residue modulo 12 is r equals 4. Since r is at most n, the count is floor of 10 minus 4 over 12 plus 1, which is 1. So only k equals 4 works. We are going to find how many rational terms appear in the expansion of the expression. The 5th root of 3 minus the 7th root of 2, all raised to the power 24. Step 1. Write the general term. The general term of a binomial a plus b to the n is t sub k plus 1 equals n choose k times a to the n minus k times b to the k. Now apply the rule to our expression. Since we have a minus sign, each term also includes negative 1 to the k. Here, a is the 5th root of 3, and b is the 7th root of 2. Step 2. Rewrite each radical as an exponent. The 5th root of 3 is 3 to the power 1/5, and the 7th root of 2 is 2 to the power 1/7. For a term to be rational, both exponents must be integers. So 24 minus k over 5 is an integer, and k over 7 is an integer. Start with the simpler condition. K over 7 must be an integer, which means k is a multiple of 7. In the range 0 through 24, the candidates are 0, 7, 14, and 21. Next, we require that 24 minus k over 5 is an integer. We can test the 4 candidates. 4k equals 0. 24 over 5 is not an integer. 4k equals 7. 17 over 5 is not an integer. 4k equals 14. 10 over 5 equals 2, an integer. 4k equals 21. 3 over 5 is not an integer. So only k equals 14 works. A quick mental check uses modular arithmetic. The condition says 24 minus k is divisible by 5. So k is congruent to 4 modulo 5. Among the multiples of 7 in our list, only 14 is congruent to 4 modulo 5. Therefore, there is exactly one rational term in the expansion. Quick challenge. Find the explicit rational term by substituting k equals 14 into the general term. Summary. In this lesson, we will find how many rational terms appear in the expansion of open parenthesis square root of 2 plus fourth root of 3 close parenthesis raised to the 100. First, the general term rule. T sub k plus 1 equals binomial n choose k times a to the power of n minus k times b to the power of k. Step 1. Write the general term for our expression. With n equal to 100, a equals square root of 2, and b equals fourth root of 3. The general term is t sub k plus 1 equals binomial 100 choose k times square root of 2 to the power of 100 minus k times fourth root of 3 to the power of k. Rewrite radicals using exponents. Square root of 2 is 2 to the power 1/2. Fourth root of 3 is 3 to the power 1/4. For a term to be rational, all exponents must be integers. So 100 minus k over 2 is an integer, and k over 4 is an integer. Step 2. Determine values of k. From k over 4 an integer, we get k equals multiples of 4. So k equals 0, 4, 8, and so on, up to 96 and 100. Rather than listing, write k equals 4m, where m is an integer. Step 3. Check the other exponent. If k is a multiple of 4, then k is even, so 100 minus k is even, which makes 100 minus k over 2 an integer automatically for these k. Step 4. Count how many k work. From k equals 4m between 0 and 100 inclusive, m runs from 0 to 25. That gives 26 values. Final answer. There are 26 rational terms in the expansion. Let's celebrate that result. Quick challenge. Can you name the first 3 k values that work? Solve the problem. Find all rational terms in the expansion of open parenthesis the 5th root of x plus the 3rd root of y close parenthesis to the 7th power. Step 1. Write the general term of a binomial expansion. For a plus b to the n, the general term is t sub k plus 1 equals n choose k times a to the n minus k times b to the k. Here, I was x to the 1/5, b is y to the 1/3, and n is 7. So t sub k plus 1 equals 7 choose k times x to the open parenthesis 7 minus k, close parenthesis, over 5 times y to the k over 3, with k from 0 to 7. Step 2. Determine the conditions for a rational term. For the term to be rational in x and y, the exponents must be integers. That is, open parenthesis 7 minus k, close parenthesis over 5, is an integer, and k over 3 is an integer. Step 3. Scan values of k. Because k over 3 must be an integer, k must be a multiple of 3. From 0 to 7, the possibilities are k equals 0, 3, and 6. Step 4. Check whether 7 minus k over 5 is an integer for these candidates. 4k equals 0, 7/5 equals 1.4, not an integer. 4k equals 3, 4/5 equals 0.8, not an integer. 4k equals 6, 1/5 equals 0.2, not an integer. None of the candidates produce an integer exponent on x. Quick insight using modular arithmetic. From k over 3 integer, we have k congruent 0 modulo 3. From 7 minus k divisible by 5, we have k congruent 2 modulo 5. Solving these simultaneously gives k congruent 12 modulo 15. None of the values 0 through 7 satisfies this, so there is no such k. Answer. There are no rational terms in the expansion. In this lesson, we will find how many rational terms appear in the expansion of cube root of x plus 5th root of y, all raised to the 13th power. Then we will write the explicit rational term. First, recall the general term of a binomial expansion. T sub k plus 1 equals the binomial of n choose k times a to the n minus k times b to the k. We will apply this with the equal cube root of x and b equal 5th root of y. A term is rational if the exponents of x and y are integers. So we require 13 minus k over 3 is an integer, and k over 5 is an integer. From k over 5 being an integer, and 0 less than or equal to k less than or equal to 13, the possible values are k equals 0, 5, and 10. Now we test 13 minus k over 3 for each candidate. For k equals 0, 13 over 3 is not an integer. For k equals 5, 8 over 3 is not an integer. For k equals 10, 3 over 3 equals 1, which is an integer. Therefore, only k equals 10 works. Conclusion: there is exactly one rational term in the expansion. Quick challenge: can you write the explicit rational term by substituting k equals 10 into the general term? Pause to think. The term is t sub 11 equals the binomial of 13 choose 10 times x to the 1 times y squared. Since 13 choose 10 equals 13 choose 3 equals 286, the rational term is 286x times y squared. We will find how many rational terms appear in the expansion of open parenthesis square root of x plus fifth root of y close parenthesis raised to the power 32. Step 1. Write the general term of a binomial. The rule is t sub k plus 1 equals n choose k times a to the power n minus k times b to the power k. Now, apply the rule to our expression. Step 2. For a term to be rational in x and y, the exponents must be integers. That is, open parenthesis 32 minus k, close parenthesis over 2 is an integer, and k over 5 is an integer. From the first condition, 32 minus k is even, so k is even. From the second condition, k must be a multiple of 5. Satisfying both means k must be a multiple of 10. Step 3. List candidates for k from 0 to 32 that are multiples of 5. They are 0, 5, 10, 15, 20, 25, and 30. Now keep only those that are also even, that is, multiples of 10. We get 0, 10, 20, and 30. Step 4. Count the valid values. There are 4 rational terms in the expansion. Optional check. Let us write the explicit forms by substituting k equals 0, 10, 20, and 30 into the general term. Summary. General term equals n choose k times x to the power 32 minus k over 2 times y to the power k over. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.